Alright guys, stat 1150 again, hypothesis testing, the 4 steps that we're going to carry out. Now what I want to do in this video, okay, the next 2 videos I'm going to illustrate something called the p-value approach and the critical value approach to work the same problem exactly. But what I want to do before we get there is I just want to run through the 4 steps that we're going to use to work a hypothesis testing problem. Now, the very first step that we implement is to state our null and our alternative hypothesis. The guys remember from last video that H sub O is the null hypothesis, H sub A is the alternative hypothesis, and I gave you a pretty thorough introduction of how you set these things up. So I'm going to assume that you're old pros at that now and know how to set up a null and alternative hypothesis based on the previous video. The next thing you do is you get prepared to implement the test. Now, for right now, I want to focus on hypothesis testing for a population mean. Now, next week we're going to get into hypothesis testing for a population proportion. But right now, I kind of want you to put that on the back burner and not be concerned about it and have tunnel vision that we are going to investigate problems only for population mean. Okay? So, we want to get prepared to implement the hypothesis test for a population mean mu. Well, the first thing we do is we check our conditions. The conditions for a test of hypothesis, again for a population mean, is we need a normal distribution or a sample size of 25 or more. Now, if you have a normal distribution and a sample size of 25, fine. But if you have a sample size of, say, 10, then you must have a normal distribution. If you have a sample size of 35, it doesn't matter whether the distribution is normal or not. Central limit theorem kicks in, and our distribution of sample means will become normal. But we either need a normal distribution or a sample size of at least 25. Guys, we need randomness and we need independence. The second thing that we do in getting prepared is we state our level of significance. Now, level of significance, I want you to think from the previous video, this is your line in the sand. This determines the cut, if you will, for a sample being close enough or too far away from the population claim for us to end up making a decision of we don't believe the null or we do believe the null. So this is a level of significance. Our level of significance is always given as alpha. So alpha is the level of significance. And guys, alpha is usually set at one of these levels. It's usually set at 0.01, 0.001, 0.05, or 0.10. Almost always you will see your level of significance set at 0.05. Now this turns out to be something we call the probability of a type 1 error. More about that later. But our level of significance will almost always be one of these values. Now, it doesn't mean that my math lab might not just throw a curveball at you and set a level of significance of like 0.07. If it does, go with it, okay? But typically in research, your level of significance will be 0.05, and if it's not, it'll be one of these other 3 three measurements. Okay? The third thing we do is we collect our sample data and compare to the claim in H sub O. Now, again, focusing on population means, what we do is we calculate and conduct what's called a t-test. And in comparing our sample data to the H sub O, we calculate what's called a test statistic. And this is called a t-value. The test statistic from a t-test is called a t-value. The test statistics from a z-test is called a z-value. The test statistics from a chi-square test is called a chi-square value. So whatever the test that we're conducting, that's the kind of what we call the value, the t-value. And we end up calculating what's called a p-value. Now, a p-value is just the probability that we get this particular sample if our null hypothesis is true. Okay? Guys, it's a lot going on with hypothesis testing. But once we get to the illustrations, I think it becomes, well, I know it does, it gets a lot clearer. Guys, the final thing we do is we make our decision. And our decision is based on the relationship we get between our test statistic and our alpha. Guys, if our test statistic, our t-value, is less than alpha, then we reject H sub O. If our t-value is greater than or equal to alpha, then we fail to reject H sub O. In this situation where we reject H sub O, we say there is sufficient evidence to reject H sub O. In this situation, we say there is not sufficient evidence to reject H sub O. Now, the final thing we do, and I know I said there's 4 steps and I'm giving you a 5th step, so I'm contradicting myself. But typically a 5th step is we calculate a confidence interval. And the level confidence interval that we calculate depends on the alpha, the level of significance that we set up our test, we develop our test from back in step number 2. So I'm going to give you a chart here that gives you a good rule of thumb. And I'm going to put up one complete video that shows when this works and when it doesn't work. But anyway, it's a good place to start. If we have a confidence level, let's go to our alphas. Our alpha as I said earlier, will almost always be one of these 3 values. If we have an alpha value of 0.05, we're going to calculate and report a 95% confidence interval. If we have an alpha level of 0.10, we're going to calculate and interpret a 90% confidence interval. See if you can figure the pattern here. If we have an alpha level of 0.01, we're going to calculate and interpret a 99% confidence interval. So what's going on here? If you think about this as a percentage, 0.10 is actually 10%. 10% plus 90% is 100%. If you think of 0.05 as a percentage, that's 5%. 5% plus 95% is 100%. This is 1%. Plus this is 100%. So up here, you probably can see the 99.9% confidence interval would be calculated and reported if our alpha value was 0.001. Now, this only is true and only holds true when we get into a two-tailed test. Now, what in the world do I mean by a two-tailed test? Well, that's what I'm getting ready to teach you. So, one tail versus two-tail test. Guys, the tail of the test depends on the alternative hypothesis that we set up. And guys, if you go back to the previous video, I told you there were only 3 forms of null and alternative hypotheses that we could run into. H sub O mu is equal to some value. H sub A mu is less than that value. Well, that's one. Another form, H sub O mu is equal to some value. H sub A mu is greater than that value. And the third form I have is H sub O mu is equal to some value. And mu is not equal to that value. Well, guys, what happens here is, going back to the central limit theorem, we have this distribution of sample means that is built around the mean of the sampling distribution, which we know is equal to mu. So whatever this value is, we assume that we're drawing our sample from this distribution. We get some value, x bar. Is that close enough to this value to assume that, well, this value must be true, and the reason we have a difference is just due to sampling variation? Or is this value too far away? Well, what we do is we create what's called a rejection region. So in this case right here, our rejection region, because we're testing to the left, we would have a line in the sand right here where this part down here would be our reject region, and this part right here would be our fail to reject. So if we get a sample mean anywhere in this area right here, like I've drawn in this illustration, then our decision would be fail to reject H sub O. However, if we get a sample mean down in this area, then we're going to reject H sub O. What would this look like? Distribution of sample means. We're testing greater than, so our reject region is going to be above the claim in H sub O. This part up here would be our reject region. This part down here is our fail to reject region. The other one that we've looked at has not equal to. Well, not equal to isn't worried about whether it's above or below the claim. It just worries is a difference. So what we do is we create a rejection region above and we create a rejection region below. And the fail to reject region is the part that hovers around the claim in H sub O. Now, which one's a one tail? Well, it's one tail if it only has one tail. It's one tail if it only has one tail. It's two tail if it only has, or if it has two tails. So when does one tail evolve? When we're doing less than or greater than. When does a two-tail evolve? When we're testing not equal to. Guys, it's as simple as that. A one-tail test is when our alternative hypothesis is less than or greater than as the inequality sign. A two-tail is when we have our not equal to sign. Now, the hard part, which will come in the fourth video, will be, well, how do we find this value right here? How do we find this, and we call it a T critical. How do we find this T critical that serves as the line in the sand that separates the fail to reject and the reject region? Now, we know in this case that the test statistic is going to be negative because it's below the mean. Here, the test statistic would be positive because it's above the mean. And down here, we're going to have two cuts. We're going to have a negative T critical and a positive T critical because we have one of them above the mean and one of them below the mean. So guys, this gets fun. This is by far, finding these critical values is by far the hardest thing that we do in hypothesis testing. But guys, we'll get through it together, and we'll make it happen. You'll find out that it's doable if you'll just follow my videos. Okay, guys, that's all I want to do in this video. I tell you what, if you're getting prepared for the next video, go to the file called Handouts, the folder on Blackboard called Handouts, and download the handout that says, I think it says something like hypothesis testing, the p-value approach. So just go ahead and download that. So guys, I'm out of here.